Welcome once again to the Integrated Design Lab of the University of Idaho and Montana State University Fall Lecture Series. This is our final lecture for the fall series. Our spring series is in planning stages, so look for that come first of the year or sometime shortly thereafter to get that spring series nailed down. As always, I want to thank Better Bricks, Idaho Power, and Northwestern Energy for putting on the show. For those of you in the room, remember to sign in. Those of you online, you already had to. A quick reminder to those online, feel free to email kevinv@uidaho.edu questions. And a quick reminder to you folks, if we do get questions from in the room or online, please try to speak into the mic so that they can get relayed to the folks online. And one quick note on upcoming events. I'm not sure if any of you have seen this through your professional channels or not, and something that the University of Idaho and Boise State, God forbid, they are actually collaborating on something. So the Department of Architecture and the department at University of Idaho and the Department of Construction Management, I believe it is, at Boise State University, have gone together for a professional development opportunity. It is a for-fee event. It's 5 or 6 Saturdays, starting in January 19th, and then it's like the 3rd or 4th Saturday of January, February, March, April, and it's an all-day thing. And covering various topics. Presenters include myself and Ari and Sherry McKibben and a few folks from BSU and Construction Management, Rebecca Mirsky and others. So for you or your clients, you might want to show them that. There should be forms available in the back. And with that, thanks for coming. And I want to introduce Dr. Ari Janadi at the lab here and Steve Pavlick with Inside Architects. They're going to be talking about local architect office building where they were going pretty far in trying to do some natural ventilation. A lot of green strategies in general, but natural ventilation specifically is what they're going to be talking about tonight. And as Ari and Steve will discuss, the folks at Insight have been really kind in letting the lab come in and kind of tinker around in their space and do 2 studies now for two consecutive summers. And Ari will get into the details, I'm sure. So I'll leave it at that. Steve, thanks for coming. Ari, good work. And I guess we'll leave this here. So take it away.
Right, thanks, Kevin. Good evening, everyone. I changed the title a little bit just to reflect what I'm going to discuss tonight. We are going to cover passive coolings, and specifically we are going to look into thermal mass, night flush, and natural ventilation at the Inside Architect's office. This is what we have for this evening. I will start this off, and then Steve will take over and discuss what is the design philosophy of that building and how it looks and how it operates. And then I will take over again and cover some background information on natural ventilation, and then some theory behind the thermal mass and night flush. And then I will cover 2 studies that we have done in the office, 2 summers of 2006 and the last summer. And then we'll go to some conclusion. So, Steve.
Thanks.
Well, I don't know if some of you have seen this building over on Broadway Avenue. It's a project, a small office, about 1,500 square feet, that was designed and built to take advantage of the solar south-facing facade and trying to get as much natural ventilation and lighting into the whole building. This is the building across the driveway from us, and there's a couple shots in here to give you an idea of the construction that was going on during the era. It's a fairly simple building, just the shed roof coming up, 10-foot plate on the low side, 2x6 framing, and then LVLs, 2x8s to get our 23-foot high wall on the south side. And then we have our mass on the east and west elevations. Here's that same building looking west with the cow wall and windows in and just shelled in at that point with a slab on grade. That's the east facade with the cow wall. As you will see in some of the interior shots, the cow wall provides an incredible nice lighting, even lit through the whole building. You don't get a lot of the glare and so forth coming through. It's a really nice, pleasant light coming through. The project was sited to have common access for both of those buildings. We sited the project up towards the street and all the parking's behind, so you don't see it as you come down Broadway at all. And both of them have the south-facing exposure. The owner who is just finishing up is a separate owner, and he's got a separate type of business operating in there, and kind of a showroom is what he's got set up in there right now. And he's been very happy with the energy efficiency of the building and lighting from his standpoint on that. Here's our entry reception desk. As you can see, that's all north-facing glass with the entry coming in 10 foot, and as you'll see here, the ceilings slope up at a 5 and 12. That's our conference room with a west-facing glass and north, the two glasses on our north side. We have, I don't know, we don't have a pointer here. The wall to the left as it goes up to 10 feet, and above that, we have glass fins that are on pivot points. So that gets, is it the mouse? There we go. This wall here at top of that crown molding goes up for about 4 feet that we have glass fins that are on pivot points, and which we allow so we can open those up and still get the natural ventilation coming in from the windows on the north side and going back up through the whole space. So all our windows are single hung casement windows that we can operate and open and close as needed. And the glass also helped quite a bit for the acoustics and privacy in the conference room. Having those closed surprisingly well worked fairly well. Again, there's that glass, and this picture was an early picture before we had it installed, but right here was all the glass fins that are operable, which we can just rotate. That's east facing, or the west facing cow wall. Here's our clear story windows that are hand cranked controls right there, and we got a long 23-foot or 20-foot pole to try to operate those things. And that's been a challenge at that height to open and close those. I think future plans are to come back and motorize those so those be a little bit more easy to operate. Workstations and everything else all between is fairly open. We have a few bookshelves that kind of divide places up, but we've kept it fairly open. Typical workstations are all on the south side for the most part. The majority of them are. Operable windows that are half casements. Each individual person can come and operate those, open and close as needed for their space. Another shot looking to the south. That view is to the east. That's the east cow wall coming in. We have open indirect light. This light fixture here is our indirect light fixture that lights up that whole space. And I think we're about 80% up on that, if I'm not mistaken. Came in with a stained concrete floor on the lower level for our thermal mass on that end. Kept everything bright above to get the reflection coming in through it very well. More of the south exposure with the uplights and ductwork. There's 3 ceiling fans up above that we use, and that's been a noticeable difference when we turn those on or off and how those operate. It makes a big difference. Bill operate those when we need to. And there's our window operator. We need a have somebody in there always operating those windows up and down. Actually, Rob has been good enough to be able to control, being bigger to help get that long pole that we need to operate those upper cases. Has been a challenge on our end, on that end. So I believe that is. Last slide. Going the wrong way here. I'm taking you back the wrong way, Barry. I think that was the last. Went the wrong way. Which way? We're going back. I want to get back to that last slide. That's 32. There we go. There we go. So that's the last shot on that end. So at that point, I'll leave it over to Terry to go through these two studies in more detail on what was they found and see if this design actually works the way it's supposed to.
Right. Thanks, Steve. Let me start with some background information on natural ventilation. First of all, about the thermal comfort range. If we look here to this chart, we have several range. The first one is this chart is basically the indoor air temperature on the vertical axis and the monthly mean temperature. So in winter, where you have low monthly temperature, you will have lower indoor temperature. So we have range A here is the for air-conditioned buildings. We can see that the indoor temperature is relatively constant all over the year, throughout the year. But if we look at the ASHRAE comfort zone, on the range B here, we actually have some variation throughout the year, from 22 degrees in centigrade all the way to 24. We have 2 degrees range between the winter and the summer comfort temperature. But then if we look at the standards for natural ventilation, where we include the adaptive comfort theories into the ASHRAE traditional comfort zones, we can actually have more room to maneuver in designing indoor spaces. For summer design condition, we can actually move from the traditional 23, 24 degrees centigrade, which is around 70. We can move up to 32 here, which is around 80, 82. So it's if we look at the 90% acceptability limit, it goes all the way slightly more than 30 centigrade. So this chart is just to show us that we have rooms to maneuver in designing indoor spaces for naturally ventilated spaces. And for different locations in the world, we have what is called natural ventilation potential. There are two main criteria in judging the potential of one area. One is the driving force, and the other one is the constraints. And the driving force for natural ventilation potential is the wind profile and the temperature of that particular microclimate. So if we look at the wind data in Boise, for example, in summer night, we know that it is very directional. The wind comes from the certain direction. And it's also quite high in the velocity. So with this information, we know that we can use night wind to have a free cooling here in Boise. But before we make further conclusions, let us look at the temperature profile in Boise based on the TMY data. This is the 12-24 chart, which means that we have 24 hours and 12 months. And I just put the temperature in the color, and we have the numbers here. Immediately we can see that in the afternoon hours in June and July and August, the temperature gets very high. That means in this time and these hours, in this month and these hours, we cannot have free cooling from natural ventilation. But from the previous wind rows, we know that during the summer nights, we have very high wind velocity, and the temperature is actually cool and pleasantly cool. So we can have free cooling during the night if we design our building properly. And now let us look at the constraints of the natural ventilation potential. The obvious constraint is the air quality of the background air in the outside. We see here one simulation on the pollutant propagation throughout the urban area. If we have this kind of situation, of course, we don't want to consider natural ventilation, which will introduce very high pollutant concentration into our space. And the next one is the noise level. Natural ventilation involves opening of the windows and any kinds of openings in our facade, which will introduce the noise from the street directly to our space. Depending on the use of the space, then this will limit the use of natural ventilation. Some spaces cannot have very high noise level in the space. And also the layout of the urban environment. If you look at this 2 CFD simulation, if we have not too crowded urban environment, we can still have some sort of recirculation here in the areas behind this building if the wind blows in one direction. But if we have high density urban area, then we immediately have stale regions here where the wind simply do not move. And this reduces the natural ventilation potential. And the NIA, the Pavlick, have sponsored studies. One natural ventilation study back in 3 years ago. The report is called Natural Ventilation in Northwest Buildings, and this is one of the charts in this book, which shows here for Boise, Idaho. Let us look at the blue line here, which is the percentage of time where we have less than 82 degrees Fahrenheit from 9 to 5 for 365 days. So office hours. We have in Boise around 90% of the time. if we change the operation hours to all hours, 365 days, then we move to the red lines. Our percentage of time move slightly up. But let us look at, for example, if we limit the operation of the building 7 a.m. to 3 p.m., excluding June 15 to September 15th, which is the normal operation for schools. And then we immediately have 97% of the time where the temperature is less than 82 degrees. 82 degrees Fahrenheit is a very important cut-off criteria where we can expect to have a free cooling from natural ventilation. This chart suggests that our schools, if properly designed, we don't need cooling, or at least we don't need as much cooling as we have now in our schools. And the next slide shows the different temperatures, outside temperatures, for different cities throughout the Northwest, where we have here Boise in the second here. You can see that 77% of the time we have temperature of less than 65 degrees, which is pleasantly cool for natural ventilation. And 90% of the time we have temperature of 77 degrees. So this kind of information we should look into before we design our buildings. And of course, we don't have much data at this point to do a full-scale natural ventilation potential for Boise. If we look at this list here, the one that is included in the report probably only covers the wind profile and the temperature. But we have yet to consider the constraints of Boise. And that we will look into in the near future. And next, let us look into cooling within the design context. The traditional way to design cooling system is the architect comes to the engineer with the complete set of drawing and say, this is my building, and the engineer will immediately design the mechanical cooling. But that should be the practice of the past. Now we promote what is called the integrated design method, where architects and engineers work together since the very beginning of the design. So with this view, then we don't simply move from building form to mechanical cooling. But before mechanical cooling, we would consider several things. First of all is load reduction, where we discuss various architectural elements with the architects that might reduce the load. And after we have an optimized design, we can still consider some passive cooling strategies, which include the thermal mass, night flush, natural ventilation cooling, even evaporative cooling. These are the non-compressor cooling, which is cheaper in a way. So if we consider these two things, load reduction and the passive cooling, then what we have is a very small load to be covered by the compressor, by the mechanical cooling. So, in this presentation, I will show how thermal mass, night flush, and natural ventilation can reduce energy consumption in inside architect office. Some background theory on thermal mass plus the night flush. I do a very simple simulation on inside building and look at different configuration. The first one, the pink one, is the building without thermal mass. No thermal mass, and no night flush. And the yellow line is with thermal mass. That means concrete floor, because that's the only mass that the inside office has. Concrete floor, but no night flush is the yellow line. And the blue line is thermal mass with night flush. By night flush, I simulate around 10 air change per hour between midnight to 5 a.m. in the morning. So we introduce lots of outside air when the outdoor temperature is cool. So what we have is, without the thermal mass, the peak temperature on the 15th of July is very high, way higher than the outdoor temperature. And then if you introduce the mass, you will suddenly have an peak indoor temperature that is less than outdoor temperature. This is the difference between this, the peak of the pink line and the peak of the yellow line, is the free cooling that we have by introducing the thermal mass. And the difference between night flush and no night flush, we can see here the indoor temperature for the blue line with the night flush is lower in the beginning of the day because we have flushed the space during the night before. So with thermal mass and night flush, we have lower peak. Sometimes this is not always the case. I mean, the peak indoor temperature that is lower than outdoor temperature is not always the case for every building. It depends on the amount of the thermal capacity of the concrete. And we also have a delayed peak, where the peak of the indoor temperature is different, slightly delayed than the outdoor peak. This is important because when we have a very massive building, the peak can move away outside the office hours, where we don't have to consider any cooling anymore. So our target is how to reduce this peak, the indoor peak, and how to move this peak further away from the office hours. If we look at the floor temperature, with thermal mass, we can see that the floor actually absorbing heat without increasing the surface temperature. If you look at the temperature, the floor temperature without the thermal mass, whatever it absorbs immediately reflects on the floor temperature. But with thermal mass, whatever it absorbs, the increase in the temperature is very minimal. So these are the advantages of thermal mass that we want to and the next slide here is, with air conditioning. I introduced the air conditioning to the simple building, and what we have is 25, which is 25.5, which is 78 degrees Fahrenheit during office hours. And if you look at the indoor air temperature here, there is not much difference between the three cases. Even if you look at the floor temperature, there's not much difference here. But if you look at the cooling load on the day, we can immediately see the difference. The difference is that first is the peak. We can see the reduction of the peak. No thermal mass, the purple, the dark line here, has a very high cooling load, and the pink is the thermal mass without night flush, and the yellow is the thermal mass with night flush. As you can see, there is a reduction in the peak cooling load. Put it simply, we don't need big air conditioning. We reduce the first cause based on this. And the second one is that if you see here, the cooling load for thermal mass is actually delayed by probably 1 or 2 hours here, which means that the air conditioning operates 1 hour later with the thermal mass cases, which is the energy savings potential. And here is the comparison between the cooling energy on that particular day. The thermal mass and night flush can save probably 60, 50%, almost 50% of the energy. Now let us look at the study that we did in summer 2006. It was a full-scale experiment that we did the objectives are, first one, to develop the operating procedure for the building, how the building should operate, what the occupant should do, the owner should do, with the objectives of to reduce the electricity cost. And the second one is to study the indoor parameters under different scenarios: air temperature, light level, and glare. And then we developed 5 operation scenarios to be tested. During the experiments, we basically just throw in sensors all over the place which measure the air temperature and relative humidity, and also we measure the energy consumption in the air conditioning units. And we test one scenario for the whole week. So we have scenario A, we use 24 hours air conditioning. So no natural ventilation. For scenario A, we test how the building will perform under worst case scenario, which is 74 degrees all day, 78 degrees all night. And scenario B is an operation scheme that is the one that was being done when we did the study. The thing that I want to point out is that the windows, the lower windows were closed under this scheme, and there was a security concern that they have to leave the window closed. And if you look at the building picture here, there are windows here, and there are lower windows there, and upper windows there. I mean, the layout suggests that you want to induce the flow from here and then move up. So without lower windows being opened, it won't work. So we know that we test scenario B just to show that it won't work. So, and then for scenario C, we play around with the ceiling fans to see whether it can help or not in the saving the energy. But we want to focus on these two scenarios, which is scenario D and E, which is basically we open all the windows during the night here. The only difference is that at the beginning of the day, we close the window at the lower windows while we open in the other scenario. This is to emphasize that from scenario D and scenario E, we move towards restricting the air from coming in by closing the lower windows. We will see that this is actually an important thing to look into. And this is our first constraint, is that we have 6 weeks of study and we have very different outdoor conditions. And immediately we have a question how to normalize the data. If you look at the outdoor temperature during for different scenarios, we actually have quite a big range here, where 2 of the scenarios were carried out in very cool week. So how are we going to compare? We will come to that in a bit. If you look at the indoor temperature for different scenarios, especially the blue lines, you can see that it reached 78, which is the cooling set point, very late in the day. It's like 3 p.m., which means that the air conditioning will start to kick in at 3 p.m. during that day. Compared to another scenario C, for example, it's immediately 80 since 9 a.m. in the morning, which means that the air conditioning is on at that time. So this is how it looks. This is the electrical load from the air conditioning unit. If you see the spikes, that means the air conditioning unit is on. Scenario B, the air conditioning unit is on for the first time right after noon. And here is scenario D, and here is scenario E. We have a control glitch where we have air conditioning on after 6 p.m., which we don't want here. And we normalize the data later. This is the result. For scenarios B and C, we see here that the air conditioning still on after 6 p.m. So we just cut this out, any energy consumption after 6 p.m. from the air conditioning unit. And we have the comparison between B, D, and E, which looks good. It's like 70% savings between scenario B, the existing operation scheme, and the one that we propose, either D or E. Even E has already like 50% energy savings. But then there is a catch. If you look at the climate data, the degree hours for scenario D and E is very low compared to scenario B. The degree hours is the hours above a certain temperature, which shows how big is the cooling load. So the lower the degree hours that we have, the lower actually the cooling load. And the way we normalize it is to take the different degree hours for different scenarios and assume that everyone have 200 degree hours, a very hot day. And then we have correction factors here. And with the correction factors, we have two performance indicators. The first one is the time delay. Time delay means how long the air conditioning unit will start to kick in, to switch on after 8 a.m. in the morning. The bigger the better. That means scenario E is the best because it delays further the air conditioning unit. And the second one is the energy. We see that also the scenario E has better performance compared to the other scenario. So compared to scenario B, scenario E delays the AC twice as long and consumes almost 3 times less energy.
Gary, it might be worth pointing out the difference between scenario A and scenario B real quick.
Okay. Scenario A is the worst case scenario where we have a typical building that operates 24 hours on air conditioning. 74 degrees during the day, 78 degrees during the night. So
Lights on.
Yeah, lights on and everything is on. So worst case scenario. We just put this as indicator that, well, just by tweaking the operation scheme, we can save a lot of energy from 92 down to 6, which is very contrast. So the lessons learned from this study is that the night flush can reduce the need for mechanical cooling. The night flush, because we already have the thermal mass in the floor. So the question now is whether we can introduce the night flush. And we showed that scenario D and E, which is night flush, can reduce the need for mechanical cooling. Okay? Now, the key word here is by opening all the windows. So the windows need to be open during the night so that we have full air exchange. And then another lesson that we learned is that we don't really have a specific, well-defined parameters to compare between scenarios. How to judge that a scenario is better than another scenario? We can have several of these parameters. Is it the cooling power? Is it the indoor air quality? Is it the amount of heat stored? Is it the time delay to the air conditioning? And these are the things that we looked into, and we propose them to as the performance indicators of the night flush and thermal mass system. Now, the problems from the first study was that the watt meter is not properly installed. So, yeah, the watt meter is not properly installed. So the absolute number did not reflect the actual watt hours. However, the ratio will be consistent. Of course, if you see the reduction 30%, that will be consistent, 30% savings. But the absolute is not. Then we decided that we need to do another study just to get it right. And the second thing is that when we talk about night flush, how much air do we need? How much air from outside really blows into the space during the night? We want to know how much. And we didn't do anything on that area. This is a very important parameter. 3 ACH, 3 air change per hour for the whole night compared to 10 air change per hour will make a big difference. And we want to study that. So we now focus on 2 operation scenarios. The first one is the existing scenarios. And the second one, the proposed scenarios, is not really scenario D and E in the previous study, but we want to really limit the air exchange during the day. So we close all the windows during the day. And this is how it looks. Oh yeah, in the previous study, we only measure the watt hour, the energy for the air conditioning unit. For this second study, we also put the current transformer into the fan unit inside the mechanical room, and also in one of the lights. If you look at the energy consumption pattern, the yellow dots indicates that the air conditioning unit is on, and it operates at the same time with the fan. So yeah, we know it's connected. But what is interesting is that the light consumption is so low, which practically means that it's never used during daytime. Which says a lot about the daylighting strategies in the office. Out of 3 days that is presented here, it's only on in the early hours of the 3rd day. So. And if we compare between the 2 scenarios, this is the baseline scenario and this is the proposed scenario, you can immediately see that this ups and downs is much thinner than this, especially this one. This is very thin, which means that the operation hours of the air conditioning unit is much shorter for the proposed scenario. But then again, we have the degree hours, which unfortunately, the proposed scenarios were carried out on a very cool week. Very cool week. So, if we want to compare, so comparing this and this is not fair, because the cooling load is so much different. So if you compare the similar degree hours, which is on the third day, we can see that there is a 40% savings on the total energy, not only for the air conditioning, but for the total energy consumption. And the next one is the air exchange study. And this is how it looks. Basically, we have a tracer gas, and we inject it to the room, and we operate the fans to mix it. And then we have a sensor, and the sensor will sample the gas concentration going up during the dosing period, and then we let it decay. It will decay because of the infiltration from outside air. There are fresh air coming in, then the concentration drops. And if we put this chart into a logarithmic scale, we should have a very nice decay, a straight line, where we can calculate the N, the number of air changes per hour. We use CO2 for the tracer gas, and we did it during the unoccupied hours, and the peak level that we dose into is only 2000 ppm, which is way below the harmful level for humans, and it's unoccupied anyway. And this is one of the results. During the one of the scenario, I switch on the fan, the main fan for the air conditioning unit. That means the building is pressurized from inside. And if you can see, there is a very smooth decay. And if you look at the same graph on the logarithmic scale, it has only roughly one decay. That means the building is very well pressurized, and there is no effects of outdoor wind pressure. So we have one consistent air change per hour. What happens if we switch off the fan? Well, we have not a very smooth decay. If you can see here, it decays and then it stops. It stops and then decays again, all the way down. And if we put it in the logarithmic scale, there is not really a single slope to represent the whole decay. I can actually make two slopes here, one here, two here. Probably there are three here. This shows that when we switch off the fan, the main fan, and opens all the window, the main driving force is the wind speed. And this will affect the air exchange effectiveness in the space. And unfortunately, I cannot present the data how much, because I haven't got the actual wind speed for that particular day. So with one more data, I will be able to say that space have this amount of air change per hour. And to conclude, natural ventilation potential for Boise needs to be studied further. We know that we have the potential, but we have some hours during the afternoon in the month of June, July, and August where we cannot have free cooling, so that it's not really straightforward natural ventilation cooling that we want to target for Boise, but we want to have a combined strategies: natural ventilation, thermal mass, night flush, even evaporative cooling. So and the second conclusion is that thermal mass and night flush can deliver energy savings, really. It's a matter of the one that we show for inside architect building is 40%, but that depends on many things, on the amount of thermal storage, capacity, and interactions with other strategies, and so on. But it can save energy. And the last one is that operational strategies, how we operate the building, needs to be developed during the design stage, so that the full use of the building is not constrained by the users being not familiar with the how the building should operate. And with that, I conclude my presentation. Thank you.
So any questions? We have a couple folks from Insight here too, so you can ask them about what's it like to live with 78 degrees, or what's it like to live with other issues related to natural ventilation. Or Ari obviously has, I'm sure, a lot more to say about some of the details, if you all have any questions about some of the details. Anybody?
Yeah, have you actually taken what you've learned here and implemented it into the building, actually tried these concepts and experienced a reduction in your energy use?
Well, that should go to Steve.
The biggest problem we had with security was one issue of opening windows at night. And what we ended up doing was putting, none of those pictures showed it, but we ended up putting blocks of wood in the frame so the windows could only open up about 8 inches or so on that end. So that helped quite a bit on that area, because we were struggling with that. How do you deal with opening the windows at night and keep secure and everything else that goes on that end? Operational, I guess, is another issue, is who opens and who closes windows all the time. That's kind of an ongoing deal of who's around. I mean, it's easy I can open up my window, my corner, and go out to a meeting, come back, it's too hot, who closes that? So there's those kind of issues that whoever's in needs to kind of keep track of that. And I think as people get familiar with how it operates, we kind of all take turns on trying to do that. Some of the other negatives, or I guess potentials, is we live in a dusty area around here, and you get the dust storms blowing through, which we've had in the past, and the windows are open and get a nice little layer of dust through the building and so forth. So those are kind of some of the issues that you have with natural ventilation in a dry climate also on that end. I mean, overall, the building has worked very well on that end. It's nice to be able to open up windows, and it ventilates well on that end. The natural light has worked extremely well on their end. I mean, the lights are hardly on in the building during our operational hours at all. I mean, evenings now, as it gets late, we turn them on in the last couple hours, and that's about it. Even in the daytime, they're turned off fairly soon, so on that end.
Do you have any problems with humidity?
Humidity hasn't been any issue at all. Another issue, a little bit, you're working on flimsy, you get a windy day, your flimsy start flowing over on the table, some of that kind of stuff, those basic things that happen. Humidity is so low here, it's not an issue in this area.
It's pretty forgiving climate.
Yeah, for natural ventilation, it's pretty ideal from that standpoint. A lot more buildings can be operating that way very easily, and keeping, as I think just some of the basic experiments they've done here, studying, it shows how much you can save just getting some natural ventilation going.
Right. I was reading an article on disadvantages of using natural ventilation in the lead project was, you know, the humidity gets in the building and then you end up with mold and mildew. So this is a good place to experiment with natural ventilation.
You know, southeast is pretty tough.
Yeah.
You know, I have family that lives down there, and they got to run the AC because of the mold issues and so forth, humidity on that end. But our morning hours here are probably ideal to be flushing out the buildings. It works extremely well. I mean, I do that on my own house. I have operable skylights and flush the building at night and then close it up as I leave and shut blinds and so forth and come home. And I'm 20 degrees cooler than the outside temperature, so it's 100 outside, I'm 80 inside pretty easily just doing that. So.
What's the experience in the winter? Do you have any benefits from this design for winter savings?
The natural light would be the biggest one. I mean, we're not, since it's too cold to be opening and operating windowless, and we get in our balmy days that we have lately here, but probably the natural light more than anything, the cow wall coming through. I mean, the lights are on maybe for an hour in the morning, I would say, right now, and then they're off until 5 o'clock, really. Being with monitors and stuff we're doing the way we're working now, you don't need as much light either unless you're doing detail work on the table, but that's probably the biggest benefit was the natural light in there during these hours when we have less natural light coming in during the day.
So I had a question about how did you come at 78 degrees? How did you find 78 degrees? Ari had presented 82 as the upper threshold of the new ASHRAE adaptive thermal comfort model. And so why 78? I know there's a little story there. Russ has told me.
Then maybe Russ should explain that one.
Story about 78 degrees.
I think we would have had an employee walk out.
If I remember, it was also at around 78 degrees, the flimsy started to stick to your hand.
Humidity took over, hand and flimsy.
But, you know, temperature, though, is really so subjective, I guess. I mean, there's days that 72 I've gone in and I feel cold, and there's days at 72 I feel hot in there. I mean, so, I mean, everybody's complained a little bit whether it's too hot or too cold on that. I think we've, as a society, has gotten our temperature range is way too thin or too shallow there. It should be a lot greater on that end, but it's interesting how some days you look at a number and you can feel one way or the other. So, you know, whether that's humidity or the way you're feeling that day, or, you know, it's interesting to check that out as the day goes on.
So why aren't there more naturally ventilated buildings in Idaho? There's one. I know of one. Anyone know?
No, that's a good question.
People's houses, right? Yeah. I know Blaine County Courthouse was going to be. It's not.
I think,
We have a nice small group here.
okay. You know, we've had two projects recently that we've been working on. One is the otopulmonary, and of course there it's a breathing issue. They've got patients that can't breathe very well. So we're filtering the air, and so naturally we can't use natural ventilation, except around the perimeter where the offices are. We are using, they're planning on using natural ventilation through operable windows. So it will be, to some degree. Security is the biggest thing. You know, another Department of Labor we're designing a building for right now, but security is a huge issue for them. And unless we come up with a good solution on how to handle that, I think that's what's preventing a lot of buildings from going to natural or night flush.
The other thing is, you know, the larger the buildings get, then they have to probably become a little bit more automated, I guess. You know, we're small buildings, pretty easy to open and close windows, but you start getting in 15, 20,000 square foot buildings and windows all over a spot. It's, you know, who's controlling that, who's opening it, when and should. You know, if we leave ours open too long, it heats up in a hurry if you're not paying attention to, especially the summer days. I mean, we start hitting 80 and you've lost what you gained in the day. You're kind of going back. So, I mean, that automation, I think, is probably part of it, too, on that end.
I might add to your question, one of the benefits during the winter is we do have some amount of passive solar that occurs. And so, like yesterday, it was really noticeable that I think our thermostat was set at 70, and I noticed when we left last night it was up to 75 in there. So you get a clear day like yesterday afternoon, and then the heat gain really starts.
Are exhaust fans considered part of passive ventilation for flushing? I saw the picture of the fan in that.
I mean, this ceiling fan or? Oh, yeah. Not in this building. No, not in this building. The airflow out of the building is by natural pressure. There is no exhaust, I think, except in the bathroom. Yeah. But in general, it can be. It can be. Though, of course, we have to consider the increase in the amount of fan energy to provide. If we provide the night flush by using fans, which is huge, of course, compared to the standard ventilation rate. Well, let's say for office buildings or for hospitals, even 2 air change per hour for normal operation, fresh air, compared to the night flush, which can be as high as probably 10, 20 ACH. If you want to cover that with fan, then the increase in the fan energy will diminish whatever savings you will have.
How does that compare to an HVAC refrigeration system, fan versus refrigeration?
You mean the numbers? I don't have it on top of my head, and I think it will be different for different buildings. Yeah. But in general, we want to target to have night flush by using passive means.
Any other wrap-up comments? Yeah, Tristan?
What kind of strategies can be implemented to maintain an air quality with natural ventilation?
What kind of strategies
Yeah, I mean, like,
can be
if you're
used?
dealing with, like, dust storms, or maybe even just air quality not being that good. I mean, are there some, strategies out there that are widely used or becoming more widely used to still maintain a natural ventilation with good air quality?
Wow, that's a tough question. I mean, the air quality, indoor air quality outside is the constraints for the use of natural ventilation. That means if air quality goes bad, we simply shut off. I mean, the experience of the people living in the desert where they have the wind catcher and everything for passive strategies, if they have a storm, well, they just shut off and close everything from the sandstorm, for example. So during that period, they just close off the natural ventilation.
Or if we have 3 weeks of smoke, that could be an issue.
Yeah, that could be an issue. Any prolonged air quality issues will be the constraint, actually.
One of the things that comes up in conversations about natural ventilation is, being careful not to try to hold it to a higher standard than we hold any mechanical system, or I should say any ventilation system, whether it be passive, hybrid, or full mechanical. Because I'd say it's the exception rather than the norm that we're actually doing a high level of filtering on our indoor, or on our supply air. And so basically the best air that we have to deal with is the air that's outside. whether that's pushed through pipes or ducts or comes through a window, you're dealing with more or less the same air. Now, there are real issues for sure that are, that come into play with natural ventilation, the security, and there's window screens that we looked through as options, and we finally arrived at these window stoppers that, basically that would allow the width of a person's head would not allow a width of a normal person's head to get through to be able to, to reach around and start trying to open the window up. But, I think the reality we came to is anybody can break into anything. Depends on how bad they want to break in. And so trying to find a couple lines of defense to slow things down. There were some wire screens, but the aesthetic effects were, they were kind of expensive. And I think you ended up doing a really nice job of, they just put in some white painted stoppers, which you had mentioned. And it held the window open to about, 5 inches or so. And then there was, then there's the dust issues, and the automation issues of the upper windows. It should be nice to have those be automated. And in a bigger building, you need to. And and then depending on your, if it rains, you have to have windows ideally that would close. And if there's a dust storm, ideally you'd have windows that would close. And so, those are some of the, I guess, the more techie side of natural ventilation. And I think the biggest thing that we've come away with of looking at natural ventilation in Idaho over the last 3+ years is, some of the things that Ari had mentioned. It's going to be a hybrid strategy, probably. That's going to be the solution. And so there may even still be passive or mechanical cooling, compressor-based mechanical cooling. But hopefully it's, 20% of the tonnage that it would have been otherwise. And hopefully there's, a night flush and a thermal mass situation, and hopefully there maybe is an evaporative cooling pass in between. So I think that's where we're at with it. Ari has done a great job leading this sort of design effort, and I want to thank Insight for playing along. We got another summer coming up, and if anyone has an idea of a project, I know we've talked about the watershed building in the past. I'm not sure where that one's at, but maybe there's another study to this. Ari and I haven't quite finished putting our heads together on this study, as Ari has been sort of data crunching to get this presentation live. So more will come out of this. There'll be a formal report after these 2 summers, and so you'll have it available for your reference. If you all want it, it'll be on our webpage. So I think our goal for that is probably in the next 2 to 3 months, feasibly at least. Our goal is probably quicker than that, but this could go live sooner. So with that, thanks for coming to the fall series, folks. Look for us again here coming up in spring sometime, and happy holidays and Merry Christmas to y'all if we don't see you again before then. Thank you, Insight and Ari, for presenting. And I have to say a thank you to our sponsors. That's the end of our series. So once again, thanks to Better Bricks, Northwestern Energy, and Idaho Power for putting on a great show.